Hello, this is Lab 2 in the Fundamentals of Physics course, and it's on the motion of a falling object. The objective of this lab is to predict a falling object's motion when including interactions from the surroundings. Unlike Lab 1, we are taking the weight force and drag force into perspective.
The object I used, or my system, was a parachute. I set the coordinate plane so that the parachute was falling down on the negative y-axis. My scale was the distance between the two pillars on the stairs. Here it is. Here's my video. You can see that the parachute goes down straight near the beginning and kind of curves near the end. Here's my time data and my y-axis data. Before I go to my computer models, I want to talk about the two forces or interactions from the surroundings we use in this lab. First, I want to talk about weight force or gravity. To find the magnitude of the weight force, you have to know that it's first proportional to the mass of the object. So, shown here, you can tell that the magnitude of the weight force is equal to g, which is a constant, multiplied by the mass of the object. To find the direction of the weight force, you know that it's all down. So we have w hat, which is the direction of weight force, equaling negative j hat. J hat is the direction up. So next is the drag force, or the air resistance. To find the magnitude of the drag force, you have to know that it's proportional to the magnitude of the velocity of the object. But for this lab, we use the turbulence drag force. So for that, we add the magnitude of the drag force equal to b, which is a constant, multiplied by the magnitude of the velocity squared. It's squared because it's the turbulence of the drag force. Now next is the direction of the drag force. This is always in the direction up. So drag force hat equals j hat, which we use as up. Here's the computer model that only takes the weight force. The mass of the parachute is set here. All the other components are also set. You can see. So here's the Y loop, and you can see that the net force is only the weight force. So I'll run this now. And there's the model. It goes up the screen a bit, so I can zoom it in. So you can see that it goes in negative y axis, and the weight force depicted by the arrow is also pointing in the negative y axis. This is the computer model for the drag force and the weight force. So the parameters are set in the beginning like the other computer model. And in the while loop, you can see that the F net is W, which is weight force, plus FD, which is the drag force. So here's W, and here's FD. When I run this, you can see that my system, the parachute, or the red cone, is traveling down the negative y-axis as before. The graph also shows this. And the drag force, indicated by the blue arrow, is in the positive y direction, or up. And as before, the weight force is in the negative y direction, or down. This is my final graph for Lab 2. As you can see, the model with the drag force, which is indicated by the orange line, and the experiment, which is indicated by the blue line, are very alike. There's almost no deviation. But the model with only weight force has a large deviation compared to the tracker experiment. I think the deviation is caused because of the system I used. I used a parachute, which mainly has drag force or air resistance occurring on it. Weight force is not a big factor in a parachute, since the flap or the plastic bag that I used has air flowing through it or coming at it, the air resistance or drag force is much more effective and is a larger factor as a force than the weight force. So when I did not include the drag force in the model with only weight, the model was very different from the actual tracker experiment. This is why I think that the model with weight force only has a large deviation from the tracker experiment. We are finally on our what does it mean question. It asks that if there's a terminal velocity in any of our two models. A terminal velocity means that the drag force and the weight force are equal, which is resulting in the net force equaling 0. So I added a print statement here. This is the model with the only weight force, and it prints out the net force. So when I run this, so you can see that the net force does not equal 0 at all. Similarly, in the model with the drag force, I added the print statement which prints out the net force. So when I run this, you can see that the net force comes really close to being 0, but it still does not reach 0. So this means that this model also does not have terminal velocity. So the what if question is, what if the object was thrown downward instead of dropped from rest? Will there be a terminal velocity? So when I run this, you can see that the system gains speed as it goes down. So if the object was thrown, it would just gain more speed, but the object would still keep moving. So I believe that there still would not be a terminal velocity,